This last section is about the power and energy. Let's gonna start with the capacitance. This is a charge Q multiplied by a voltage V. An electric current is a charge per time. Then we have also Ohm's law, the EMF, voltage, the drop of a potential between two nodes equals the resistance of that node multiplied by the electric current passing through. Today we will see what is a power. A power is a voltage multiplied by the electric current passing through resistance, and the electric current, that would be the same as I squared times resistance. And if we use the voltage, no current, so that would be voltage squared divided by R, resistance. So all of these are given as the formula for a power. The unit of a power is watts, or just we can just use W, watts. Now the last formula is, if you want to calculate the power energy, that we can represent with PE, or sometimes to make a distinction between potential energy and power energy. This is also a kind of a potential energy. So the unit is joules. So that would be the power multiplied by time. So this is a power in a given time. So we call that watt second. Since the watt second is really small, so we may use most of the time the kilowatt hour is the power energy in 1 hour. So this is per given time. So these are all of the equations that we're gonna use in this last section. Power of energy, so PE, this is a power times time. The power in an electrical circuit, so basically this is between two nodes. So if you have the voltage and the current, then you multiply voltage by current, the unit would be W, watts. If you don't have voltage but the current and resistance, so that would be I squared times resistance. And if we have only voltage and resistance, so that would be V squared divided by R squared. And of course, we have seen before Ohm's law. Ohm's law, V equals R I squared, and the capacity and electric current. So in general, if you want to study a simple electric circuit, we have to talk about electric current, resistance, especially resistance equivalent. If we have a complicated circuit, we can talk about power, and we can also talk about power energy. I will give you a very simple circuit. Then we will try to solve the electric current, the resistance equivalent, or the electric power, or the power just this can be for the whole unit or just one portion of the electric circuit. So here is a simple circuit that we're gonna study here, just the basics. So we have the switch here. We have a resistance. So let's say this resistance is 6.0 volts. Let's say we can put a simple lamp here. And we close the circuit. Now 12 volts. We have resistance 6 volt and the lamp. So the lamp is just to test if it is on or not. Then let's see where is the electric current direction in this case. So since this is positive, this is negative, so the electric current is moving in this direction. So that's I. Let's call this I. So we're gonna find this electric current. What is the value of this electric current? So I from Ohm's law, I equals 12 voltage divided by 6.0 of the ohms resistance, and that is 2.0 amps. So this is not very difficult to do. Now, what is the power? What is the power at the resistance? So that means we have the difference of potential in this case, which is 12. So if you want to calculate the power at this stage here, so 12 squared over resistance, and that will give us 24 watts. Now let's say that we want to have a light 30 minutes, half an hour. So 30 minutes, we have to convert it into seconds. So that would be 1800 seconds. Then we multiply the 24. So if you want to know what is the power energy, if you want to know what is the power energy at this level of the resistance, which is actually for the whole circuit because we have only one resistance here. So we just multiply P, 24 watts, then you multiply by the time we are running it. So that gives us 43,200 watt seconds. And since this is a big number, so we can round it up to 43.2, let's say, kilowatts second. And kilowatt second, and as it is expressed in watt seconds, watt second is joules, so you can also express this as kilojoules. So this is the energy, 43.2 kilojoules, running this lamp in 30 minutes. In this case, we study just one resistance. If I change it a little bit this way, so I'm going to keep exactly the same numerical values, but we're going to make two resistance in parallel in this case. In parallel, but that's going to be the same value. To make it 6 passing through here, we're going to make it 12 ohms. And this one is also 12 ohms. The equivalent in this case for the two parallel here, that would be 6. That would be 6 ohms. So what does it mean? If we keep the same values, let's say 12 volts here, 6 ohms, 12 ohms, 12 ohms, but again, that is the equivalent of 6 ohms if you do the calculations for our equivalent for resistance. So that means we're going to keep the same power for the whole system would be 24 watts. And if you want to keep the same time as 30 minutes, same thing, we're going to end up with 43.2 kilojoules or kilowatt seconds. Now, This is for the whole system. Those two are equivalent. But what happens is, if we divide it into this resistor here, so we have on one side, that's the 12 here, and we have on one side the other one here, which is this is the same thing, 12, same numerical values. So this one single branch here would have 12 watts, and the other one would have 12 watts. And when we add those two up, then you get the 24 watts here. 12 watts is the power for one branch of resistance. The other branch is 12 watts as well. So when you add the two up, then you get for the whole system 24 watts. So we add up these energies. So this is a simple one. We will try to solve a bit more complicated than this one next time. So if you just pay attention for this power and the power energy here, and then we would be able to solve a little bit more complicated circuit.